Well, welcome back, everybody. So thank you again for putting up with all the experiments. I think most of them worked. The whiteboard clearly didn't. So I have a temporary whiteboard solution today if we need it, and some more experiments that I'm doing. So today's topic is about the hardware. So I guess sort of the right place to start is describing the robot we've picked for the class. It's virtual this time, but it's still, we've made it a choice that we're going to mostly think about the particulars of the robot you see on the screen and a slightly nicer version of the hand you see on the screen. But it's one of many robots that are out there. And I want to, if there's one thing that I want to accomplish this today is you have a better sense of the spectrum of robots that are available for this kind of work, why we picked this one, how it's different, and maybe a kind of a sense of whether it's the hardware is holding us back or whether it's sufficient for the task. Okay, so let's dig in. So again, Terry, I hope yeah, good, thank you. You're putting the slides.com stuff up. So getting a little, maybe more slick on this. So this is on your web browser. If you have the slides.com open, you can click right there on the web browser, and that'll open up your your Colab binder, get you ready, and then the first step is then to click here on your screen. I was trying to make it clear that one of them is actually on your screen, one of them is just my representation of your screen. But on the other window, just hit play on that first cell, and it will provision the cloud machine. It only takes like 2 minutes, but might as well do that now, and it'll be ready when we get to it. Okay, so again, today is we're going to give a survey of robot arms. Talk about the EWA in particular, this particular robot that we've chosen from KUKA. There's a couple different EWAs, but we actually oscillate a bit back and forth between the EWA 7 and the EWA 14. They're just they're very similar. I want to tell you some of the subtleties. We talked about it a little bit last time, but I'll tell you a little bit some of the subtleties so you just have an appreciation of what's going on in order to simulate that KUKA and visualizing the results. We're going to do some breakouts to see if you can mess around with that a little bit and interact with people in the process. We'll come back and then we'll talk about, you see the KUKA is great, but it's got a stub at the end of it, right? So there's a second question of what end effector, what hand or hand-like thing appendage would you like to put on your robot? And we picked a very simple gripper for the class, for most of the class. We'll talk a little bit about more dexterous hands later. And the particular one is called the WSG, and we'll tell you a little bit more about that. And then make sure you, kind of understand the API you have. So if you had that robot sitting in front of you and you've got the drivers loaded up on your computer, what commands can you send? What commands do you expect to receive? And that's kind of our, today's lecture in a nutshell. So a quick question just to see if people like, have an opinion about these different robots, what robots you use so far. This one is got a couple options. You get to scroll. I'm curious if people have a particular robot that you're already using that you like. No opinion yet is totally reasonable. You didn't mention me is totally reasonable, but those are some of the common ones today. Those are the makes, not the models, I guess. But wow, I actually don't know for sure which robot is winning by so much. Maybe I have a guess, but it might be a skewed population, right? This is like it would be very different if I asked this at a logistics company or something. All right, one more second here, and then we're gonna see what the answer is. Ah, I should have seen that one coming. Okay, yeah, all right. So no opinion yet is the one that everybody's using. Okay, and everybody else is evenly distributed. That's good. That means I've got a blank slate for class. So the one I've picked is KUKA, and I guess 7 of you agree. And we'll just make sure you understand, because there are a lot of choices out there, and it's a really interesting time where you know, hardware is changing fast. So let's start digging in a little bit. So on the left, you know, we've seen factory robots for a long time. They are typically separated from humans. There's, you know, a big cage often between the robot that's strong enough to pick up a car and move it around, or spray paint a car, or, you know, somehow arc weld a car or something like this, and where people will go. And, you know, they've been hugely successful, massive, you know, massive impact on the way we can manufacture goods and everything like that. But they're very different than the robots you'd want to have in your home. And it's actually only a handful of years ago that people really started, you know, openly stating the differences in the problem of making a robot that could potentially work in the home. Rod's picture here, this is Rod Brooks and the Baxter robot. You know, that is a carefully posed picture showing that he's not afraid of being near his robot, and that's a big deal. So you know, we like to joke in robotics that you can tell how confident you are about the robot based on how close you are to the robot, right? So it used to be in walking robots that if you were far away from your robot, that meant you were confident it wasn't going to fall down. You know, you didn't have to be there to catch it. But then as robots got bigger and more powerful, like the Boston Dynamics robots, for instance, then it suddenly became more impressive if you were willing to be close to your robot, because that thing could, if it went wrong, it could really do some damage. And I think Rod's making that point beautifully with that kind of a picture. Okay, and maybe actually robots are still going to evolve a lot from here. I'm a big fan of Big Hero 6, and we actually have some folks at Toyota Research that are working hard on building something that looks like this, as are other groups. And this is a real thing. I mean, so it was actually fascinating. The director who made this movie went around to a bunch of research labs. He had actually just come off the job of making Winnie the Pooh, the movie, right? And his next movie was Big Hero 6. And he stopped by our lab at MIT. And actually, if you look closely at the big lab space, you know how in Big Hero 6, when they all walk through and there's a guy like using a laser and there's a guy doing, you know, there are all these cool things happening. Well, that big building they're in looks a lot like the data center if you look at it. In particular, the stainless steel. I think it was modeled after our building. It's also the thing that blew up like 2 minutes after it was shown. So, but the actual, you know, the robot you see here, of course, that wasn't just purely out of their imagination. They went to CMU and were in Chris Atkinson's lab and actually saw a robot that looked like an inflatable, and it was just an arm at the time. And they took that as their inspiration and made this, you know, amazing movie, right? So it was a very, I mean, I think roboticists have gotten more out of science fiction than vice versa, but this was an example of nice, like a nice marriage. And, you know, who knows exactly the role of very soft interactive robots, but I think it's a super interesting trend in hardware, and it's maybe epitomizes the difference between the factory robot and the robots, you know, the ones we're going to use for class are somewhere in between the two. Okay, so we got like a spectrum of robots. These are the ones I listed on the little questionnaire, for which you were somewhat evenly distributed with everybody except for the people that didn't have an opinion yet. So, but they're actually pretty different if you look across the spectrum. So the UR robot, that's, I had it in my head without even thinking. I was thinking, oh, maybe there's a lot of people choosing the UR robots because they are becoming more and more common. You see them in a lot of places. It's a position controlled robot. It's pretty low cost, and it's got, you know, a good workspace, reasonably good payload. There's a lot of reasons why you might pick a robot, and those are many of them. It's a position controlled robot, and one of the things that we're going to talk a lot about in the next hour or whatever is the difference between a position controlled robot and a robot that can do torque control or measure and torque sensing, okay? The KUKA is at the opposite extreme, is a robot that is trying to do torque control and torque sensing, and we'll talk a little bit about how it does that. Franca, I put over here by I'm heavily biased in my selection of robots that are more force controlled, I guess, but the ABB robot is another position controlled robot. They have many like factory robots, and this Yumi bimanual robot is one of their first sort of, they think of it, I think, as a small parts manufacturing or, a sort of a working closer with humans type robot. Rethink really tried to do something very interesting, which is making a very low cost robot that is safe to be around. Canova similarly has a relatively low cost robot that is light enough. So most of these robots actually have a big base and a control cabinet and a power supply. The Canova is special in the sense that what you see there is the entire robot effectively, and it can be mounted on a wheelchair. That was one of the big initial application areas. And it has a bit of torque control, torque sensing and torque control. Okay, so let's, I'm making a big deal of that. Let's think a little bit about what the implications of that are. So, or why do we even get there? So it turns out that if you want to use electric motors to control a robotic arm, then, well, there's a couple things. First of all, electric motors are heavy and they tend to like to spin fast. They're most efficient when they're moving at high RPMs. So there's a lot of incentive in order to have a very small motor that's spinning very fast and a big gear reduction, like sometimes crazy big, 1,000 to 1 kind of gear ratios. Certainly 100 to 1 is very normal. Okay, and there's some really nice work. Like if you look at the Asimo robot, the harmonic drives that they put in the humanoid that Honda built, just absolutely amazing hardware design. And they're making these very big high gear ratios, meaning that for every revolution, for every, let's say 100 or 1,000, depending what the gear ratio is, revolution of the motor, the shaft only moves once, right? It goes one time around the circle. That's our gear ratio. And to do that, normally 1,000 to 1 gear ratio incurs tons of friction, lots of backlash and other things from the gears where they're meshing together. So there's been, really good work on trying to make better transmissions that give you those high gear ratios, because that's where electric motors have their sweet spot. Okay. But there's a different end of the spectrum. And if anybody, how many people are in mechanical engineering here? I know I didn't ask a survey question, but there's definitely some mechanical engineers here in the audience, right? So awesome. Actually, my favorite place that I sort of felt like I learned about what it meant to be a torque controlled robot is from a book in 1987 it was actually mostly Kamal Yusuf Tumi's thesis that turned into a book by Harry Asada and Kamal called Direct Drive Robots, Theory and Practice. Okay, it's a beautiful treatment of not only first and foremost robot dynamics. You guys are lagging a little bit for me. Let me just give myself priority so that I'm not fighting with like Netflix or whatever down the stairs. Okay, so right, so it's a beautiful book. Actually, I highly recommend it. But it has inside it a very nice like opening chapter, or maybe chapter 2, I guess, that explains what it would mean to be at the opposite end of the spectrum, where instead of having 1,000 to 1 kind of gear ratio, you actually have a direct drive. You're putting the output shaft of your motor directly onto the thing that's turning. And the robots that they sort of show, I almost put some pictures in here, but the robots that they show are like these massive robots with the stators for the motor bigger than, or as big as I am, in order to turn a link that's about the same size. And it's kind of crazy, but it made the point, because those robots could be torque controlled, and the ones with the big gear ratio can't be torque controlled. Now let me try to help you understand why. So I told you that if you have 100 to 1, 1,000 to 1 gear ratio, then you've got a lot of basic, complications, friction, but also, backlash and other things that are very, very hard to model in your transmission. And what that means is if you have a direct drive motor, your motor is directly attached to the output shaft, you can basically expect the current that you're putting into your motor to be proportional to the force or torque you're getting out, okay? But if you now put this massive gear train in, not only is that thing hard to model, but any small errors that you have in modeling it are multiplied by potentially even the square of the gear ratio, but certainly in the standard case, multiplied by the gear ratio. So if you just try to ignore a little bit of backlash sort of on the first link of your planetary gear or something, that error that might have been small there gets amplified, okay? And conventional wisdom is basically that if you have a big gear ratio, you cannot assume that the current you put into the motor is a good representation of the torque that you're getting out on the other side. Now, where's the threshold for that? People will talk about different places, but so I think people talk about less than one or one or less is strict direct drive. If you're like in the 10 range or something like 10 to 1 kind of range, people will call it quasi direct drive if you're a little bit over 1, and think of it as, yeah, you can get away with calling that torque control, but it's not perfect. But then if you get up to like the 101 and beyond, then people don't think about that as having direct torque control anymore. Okay, so if you don't have direct torque control, if you cannot apply a current and expect to get a certain torque out, then how do you control your robot? Well, it's not too bad. You just put a sensor on the output shaft. What sensors can you put on the output shaft? The simplest one to put on the output shaft is just a joint angle sensor, or some rotation sensor, an encoder or a potentiometer, okay? And if you just measure the angle that your output shaft is directly, then all you need to have for your model of this complex transmission is just the idea that if I push more over here, I'm going to move this way. All you really need actually is monotonicity. You don't need a strict model, an accurate model. All you just need to know is if I push a little harder, I'm going to move a little bit more. Okay, and then you can close a feedback loop just using very simple ideas from proportional control, proportional derivative control, PID control. I wrote the basic equation in the text for you if you want to think about what that looks like. But these models make very few assumptions about what the dynamics of the transmission are, and if the gain is high enough, if you're willing to make a big response to a small error in your joint, then you can actually get pretty accurate and tight control despite having a big gear ratio. And so that's what people do. If you have a UR robot or a factory robot, you invest heavily in the accuracy of your position-based sensor, and then you close a high gain feedback loop. And in practice, the API that you give to your users is go to this position at this time, okay? Or sometimes it's over a trajectory, and you can try to control a velocity, but positions and velocities only, because people mostly believe you can measure position directly, you can differentiate it once and do pretty well, but by the time you're trying to differentiate it twice and regulating accelerations, somehow the noise builds up and people don't really trust that anymore. So, since most of these robots grew up with jobs that were defined roughly as being very accurate in position, then that was a good thing to do, and that made a lot of sense. But if you start moving through the world with Rod Brooks in your clutches, then you don't want to do that, right? Because that would suggest that if the robot was programmed to basically move to a certain position, it's going to get there with high gain, whether Rod was there or not, right? And sorry, Rod. So you got to do a little bit better. The KUKAs are actually someplace in the middle. So they do have a fairly high gear ratio. I found exactly what it was. It's around 100 to 1 or something like that, and I put it in the notes. But they actually invested a little bit more in the sensing on the output shaft. So they accept that there's a big complicated transmission, but they're actually putting strain gauges on the output shaft. And so they're not only just measuring positions, they're measuring torques directly. Now, they're measuring torques with strain gauges, like I said, but that's kind of, it used to be sort of a black art. I think people are getting better at it, but it was When these robots first came out, it was very surprising to me and to I think a lot of people, the quality of torque control that they were able to get with a relatively stiff transmission. Because basically, let me save that for a second. But so, okay, so this is now a pretty complicated transmission with a lot of electronics on both sides. But in practice, by measuring torque on the output shaft, using that to directly servo the input shaft, then you can get torque control back out. Okay, so what is a torque sensor actually? A torque sensor is fundamentally something that's measuring. It's a spring is fundamentally what a torque sensor is. And the Baxter robots are using yet another version of this, which is called series elastic actuators. And there's a handful of robots that are using series elastic actuators now. That was an idea that was popularized by Gil Pratt when working on walking robots at MIT. But the idea is, so this gives you high quality, relatively high bandwidth torque control with effectively a stiff spring in the last piece of your gear train. And Gil and others, and Rod, when he started Rethink, said, what if you put a very soft spring at the end of your transmission? Now you get large deflections. You can use actually relatively lower cost encoders and potentiometers to get still pretty good torque accuracy, a torque measurement accuracy. And then you also have a kind of a natural compliance with the world. So as you move through the world, if you bump into something, even if your controller is doing the wrong thing, there's actually a spring between you and the world. And maybe that's most of the time, that's probably a good thing. And you can close the feedback loop on that. It does compromise your bandwidth. So it means that you can't, whatever motion you're doing, when you do make contact with the world, unexpected contact with the world, you can't change what is happening as quickly as you can with a stiffer spring. You know, there's sort of pent up energy in the spring that it's going to continue to be released. But it's a very interesting sort of spectrum of robots. This is Sami Hadaden. Sami is a full professor in Germany. He's like, if you meet him today, he's just like an incredibly well put together, you know, he's going to be wearing a suit. He's super nice guy. But he was a grad student once. And he was, when he was a grad student, he was playing in the lab, the DLR, which is the German equivalent of NASA, you could think of, with the implications of trying to make robots that did have better torque sensing on what it means to have physically safe human-robot interaction. So there's a series of videos where he basically made the robot hit him, and I decided not to include it, but these get progressively more aggressive. I think if we let it go, he's going to start hitting himself in the head. And if you Google it later, you can find some that involve knives and relatively sharp knives moving at relatively high speeds towards, I don't know, something on the table, even his arm. Kind of crazy, but it made the point. And it maybe, I don't know if it made the KUKA robots successful or not. But these robots are really pretty spectacular in the sense that we can measure the torque we're putting out in the world and control the torque we're putting out in the world. So the KUKA is a more expensive robot than a UR5. It's a more expensive robot than the Baxter. For a research lab where we're trying to have a few of them, let me stop that because otherwise it'd be very hard to listen. You know, for a research lab where we need a few of these and we want to try to understand the implications of having good quality torque sensing, maybe we can always ignore the high quality or make it act worse. It makes a lot of sense for us and for this class to use a high quality robot. These are in the 80K to 90K range for just the robot. The Baxters are much cheaper, and the other one, you know, the UR10s are much, UR5, UR10s are much cheaper, but these are incredibly good robots. Okay, so any questions before I move on about, you know, torque control versus position control robots? There's actually, it's a really good time because this is changing again. It kind of happened from the hobbyist world and the people building quadrotors and hobby aircraft. They started using outrunner motors, and outrunner motors have higher torque density. they've got these really slick now frameless motors, and those have sort of pushed forward in quad rotors, and now people are starting to bring those back into robot arms. So there's actually a chance that we can get motors on our robots that are comfortable spinning at lower RPMs, cost relatively less, and we get low cost torque controlled robots. I think that's coming soon, and we're seeing it from, I gave a few examples in the notes. There's like a bunch of startups out there building what look like really exciting low cost arms, and that's going to be the next big trend is low cost arms.
One quick question.
Yeah,
where would something like the motor and drive unit on Cheetah or things like that fit into this, if at all?
Yeah, no, totally. So MIT Cheetah in Songbei Kim's lab they call that a direct drive robot. It's maybe quasi direct drive. It's probably a gear ratio just a little bit above 1, but they are building custom wound motors in order to do effectively the direct drive robot. That's also one of the reasons why you see the legs on the quadrupeds these days being incredibly light, because you'd like to have high torque density and low mass, and then you can get really good things.
I have a question as well.
Yeah.
So it sounds like most of these arms kind of rely on PID loops and controllers at the joints. Do you think there's a future in robotic arms for kind of more advanced control techniques, like more maybe explicitly nonlinear control schemes? Or do you think PID is kind of
here to stay? Yeah, that's an awesome question. Actually, it's one of the questions we're going to have you kind of dig into. I guess we emphasize the one link instead of the multi-link, but so one of the things that happens when you have a big gear ratio is that you also have a very big reflected inertia. Okay, so the equation I put up on the very bottom here, which will have you think about critically in your problem set. It's got something pretty amazing that happens here. N is the gear ratio, J is the moment of inertia of the arm, and J rot is the motor inertia of the rotor. Okay, so if you think about pulling on a pulley through a big gear ratio or whatever, so of course it makes things that feel far away from you light. But if you think about the influence of your pull on the other side, it feels incredibly heavy. Okay, that has a weird consequence here, which is the relative, even though if you were to weigh the arm, the mass of the motor feels very low compared to the mass of the arm. But the effect it has on the gear is actually dominates, because of these big gear ratios, dominates the inertial effects of the arm. So you would expect these things to act very differently if they're this area or this area, or to your point, I think you'd expect coupled control at the joint level. You wouldn't expect to control each joint independently with a PID controller. You'd think you could do a lot better if you somehow mix them all. And the reason that tends to not be the case is because when you have a big gear ratio, the gearbox not only linearizes things, but it also makes the effective mass matrix diagonal. Okay, and we're gonna try to make that point in the problem set, and we'll revisit the more nonlinear control. I'm going to actually talk about the way that they implement the impedance controller on KUKA later, which is the sort of nonlinear at a joint. But it's not the lack of math or effort. It's that actually the dynamics look pretty linear, and PID is a good thing to do.
And maybe this is jumping too far ahead, but do you think that's kind of how human joints operate as well? It kind of constructed in a mechanical way that enables linear control without like adaptive gain tuning or anything, or do you think humans move more nonlinearly?
My suspicion is that the things that make our math easy is not the same things that were designed that make it the math easy for our. Yeah, I think there's different reasons why the musculoskeletal system simplifies control. It's not like linearized reflected inertias. But I think we're still learning exactly what the answer is there. Cool, thank you for the question. Okay, so let's think about taking one of these arms and putting it into a simulator. So we're going to get to the breakout here, but let me work you up to it. So you need a physics engine. You need to understand if you're commanding torques at your joints, you have to figure out how the robot's going to move. Okay, and now it does involve potentially the inertia of the rotor, but also the inertia of the links and contact forces with the world and all these things. It's potentially a pretty complicated physics engine doing the work. I told you quickly that, but the name of the physics engine in Drake is the multi-body plant. So the word plant seems a little weird. That comes from chemistry, but it's actually, it's sort of super important to me that we called it that because it exposes our, it's not just a physics engine, it's a physics engine you can use for control, right? It's built so that you can do more rigorous control with it if you want. And the way you use it in Python is actually pretty simple, but it's going to get buried down into a diagram. So I don't want it to be mysterious later. And let me just show you that it's actually very simple to use. So you just construct a multi-body plant. There's like the basic input argument is just whether you're doing it as a continuous time model or a discrete time model. You can set time step to 0 and it would be a differential equation. That's in the noise for you, but except for the fact that when we're simulating contact, it turns out that using a small time step is probably the right way to go. 1e⁴ will get you started in the right ballpark for these problems. Then you have to load your robot into the dynamics engine. And the way we do that is we use these robot description formats. So, so this is a SDF file. I've got a version on the next slide of what the SDF file looks like. It's just an XML file that basically goes through and says, this is what an EWA looks like. It's got a link. The link has some inertia. It's got a mass. This tells me where the center of mass is. You know, this tells me the inertial properties of the EWA, and then it tells me, you can scroll down. There's an object file that defines what it looks like. It's got material properties, and it's an XML file that describes basically what the robot is. And there's only a handful out there. Unfortunately, there's not like a universal love for one of the formats, but we use URDF and SDF primarily. Okay, and it's not hard to make your own if you have your own bespoke robot, but also if you have a robot that you're using, you can probably find one of these on the web. When you download it from the web, you should be suspicious and assume it's wrong, because it's sort of amazing how often they are wrong. But you can get them in your simulator pretty quick. We have put in a handful of them for you, of the common ones in Drake, and vetted them carefully. Okay, so we do a little game because your SDFs can be anywhere on disk and stuff like this. We try to make it robust by calling this find resource, or throw means that it'll tell you if it fails. Okay, and then, so that's just bringing a robot into the physics engine. We don't want just a robot in the physics engine. We actually want it to bolt it to the ground. Otherwise you're going to find out what it does in a few minutes. And then once we're done loading things up, we just tell it we're done. And that's all you have to do to load it into the physics engine. Okay, and then now, if you've thought about differential equations or difference equations much, let me actually recommend that everybody flip now to the Colab notebook. You'll see it on my Zoom screen if you like, but I think you should be fine just looking at your Colab notebook if that's better. You've already run the first cell. But if you go to simulating the passive EWA, which there's a table of contents on the left, you click simulating the passive EWA. Okay, you can see the lines I just showed you of loading the EWA into the dynamics engine. Let's go ahead and run that line. So we've done that work. Okay. Now, the equations of motion that you're going to be using in your robot, if you've chosen a discrete time model, they look like a difference equation like this. Okay, you can have a discrete differential equation or a difference equation, depending on which way you want to simulate it. For contact, difference equations are best for now. And then your difference equation could be dependent on time. N is time in discrete time. X is my state vector. U is my command input, my torque command input. It could have parameters. It could have noise. You know, if you're a mathematician using differential equations, you will write things like this almost all the time. but you will observe that sometimes you have n, sometimes you don't have n, sometimes you have parameters, sometimes you don't. Okay, so instead of having like functions that take variable number of arguments all the time or whatever, we just took all of that and jammed it into a structure and we called it the context. Okay, so that's what the context is just make my list of arguments. So for any system, you can say create default context and you'll get sort of your structure generated. And you can print your context. It's got a time, it's got states. The EWA model has 7 links. That means it's got 7 positions and 7 velocities. So it's got a total of 14 states, okay? This was actually kind of fun because this didn't happen yesterday, but I uploaded it to the latest nightly build, and suddenly we got these parameters, which is because it's just coming online now, but it's awesome. So you don't need them in this class, but the fact that actually every link also exposes its mass, its center of mass, its inertia and stuff like that, and you can take gradients with respect to them. You can change them on the, you know, it will, if you want sort of advanced features, that's going to be super cool. But this notion of a context is sort of your, you know, your state, parameters, inputs, time. Okay, you can set the positions. For instance, we give, since that's a complicated structure, we give you like simple interfaces to set it. For instance, you can say plant, please set your positions in the context to these 7 numbers. Those are the 7 position elements. Okay, and then it'll have changed the positions to that. You can also do it one at a time. You can call a particular joint. You don't have to remember the joint names or joint orders, just set angle. Okay, and then we want to set what command we're going to send to the robot, what torques we're going to send in. And to start, we're just going to send 0 command in, say, don't apply any torque, the motors are off, let's say. Okay, so we'll just tell the context that we have 0 effort. That's all you need to run a simulation. Okay, so you can now set this up. It's going to run, you create a simulator given the plant and the context, run it for 5 seconds, and my states have changed. Now that's an incredibly boring simulation because, you know, it just changed a couple numbers, and this is a robot that lives in 3D, and we should be able to do something better than that. Okay, so we can do something better than that, but it takes, you have to bring in one more piece of machinery, which is this notion of a scene graph. Okay, so the physics engine is one part, that's the multi-body plant. The scene graph, if you've ever played with video games, these are the 2 things. There's a physics engine, there's a scene graph. The scene graph is what handles all the visualization, all the geometry, all these things. Okay, so they often come together. So we have this add multi-plant, body plant scene graph method. Okay, and you're going to put these together in a diagram. But this is almost exactly what you see now. The only difference is that we've added the scene graph also, and we've also added a visualizer, the Meshcat visualizer, the same one you saw in your teleop. Okay, so you can go ahead and open that link up now. You'll see almost nothing, but you'll see your visualizer at least. Okay, if you run the next cell, then that will tell, it'll say, hey, Meshcat published to it, and then you'll see something in your visualizer. So, you know, this thing got more complicated now. It's got 14 discrete states in the plant. It's got a bunch of parameters, but it's got an abstract state holding some of the geometry information. Okay, but it's all curated pretty carefully, and you can work with it, and you'll learn to work with it. Okay. We made our first diagram in the couple lines of code. So it's a pretty simple one. We have our multi-body plant. It has lots of inputs and outputs. It's wired up to our scene graph, and it's wired, the scene graph is wired up to our visualizer. That's what you've just done in that code. Okay. You can still set the position. The notion of context is hierarchical. So the plant has a context, the scene graph has a context, the Meshcat visualizer has a context, but the diagram has a context. If you want to get telescope up or down, you can, for instance, use these kind of methods like get my context from the root, and it'll tell you the context for the plant. And you can set the positions the same way you did before. Okay, so Now, if you run exactly the same code as before, I added one line to say run at real-time rate, because otherwise it'll just run as fast as possible by default. Then in your window that you opened up a minute ago, in the Meshcat window, you'll see the robot do something. What's it do? Anybody, are people doing this in real time? Yeah. Robot's bolted to the table. I told it 0 torque of the motors. It just falls down, right? Okay. I'm going to just give you one more trick, and then we're going to go to breakouts. But this cell those are a bunch of different cells that stepped you through it. This cell does all of that in one place, so you can mess with it and just rerun this one cell. And I added in one extra little bit, which is to record. I can tell the visualizer to record and then publish its recording, so it'll make a little movie in the visualizer. So if you look at my slides again here, let me just show you. Once, in your Meshcat visualizer, you can pull down your controls. You can save images, load images. You can also play back animations. There's a little player kind of thing to do there. So this is what I'm thinking. You guys have to help me through these breakout sessions, and I got some really good feedback from a few of you about what could go well. But there's a cool thing that happens with this Meshcat setup. You can actually, we're going to have about 5 people in a room. You can actually just designate one person as the one who's going to be doing the code changes. That person can just make a new cell or change the cells in the notebook. You're not going to hurt anything. You're not going to lose anything. You can always save to Google Drive at the end. That person, when they run it, is going to have a Meshcat URL. And you can just share it with your friends in the room. And everybody can watch the same simulation, the same visualization. Okay, so I think it really is going to be, a shared environment, right? So maybe we'll have you all as avatars in there at some point. Okay, so you can all view the same scene, and this is the challenge. So think about what's happening in the weld or in the physics engine. Okay, so if we do everything we did before, take away the weld joint. Okay, the thing that attached it to the world. So what we saw just now was the robot started in some comfortable position and it fell down like this, right? So just think, before you go into breakout, just think about what's it going to do if I take away the weld joint. Okay, and in particular, what I'd like to know when you come back is, where is the hand going to be relative to the base at the end of the simulation? Okay, and you'll need the video to figure that out. And if you have time, then you can mess with the context and see if you can actually figure out the joint angles well enough to put, command it to be in some joint angles that will put the hand, when the weld is back on, the hand directly on the ground. Okay, and I'm hoping that when you come back, I'll ask you guys to, share your best shot of the whatever happened to the robot. This is like the noisy slide that says everything I just said. But we're going to send you to breakout rooms. Now, the one last thing is, we realized last time, so yeah, I don't think we can actually drop into different rooms. That didn't work technically for us. So I think the staff is going to wait for you here. If you have questions, you can come back to us. If we have the ability to jump in, we will, but it didn't happen last time. So, so if you have any questions, come back and ask us. But otherwise, do your thing, share your screen, figure out where the hand's going to be relative to the base, and we'll see you in like 10 or 15 minutes. We'll see how long it takes. How did that work? Good. Yeah.
Reasonably.
Anybody catch it on video? Do you have you could share your screen and we could see any animation you caught or anything like that. If anybody has the moment captured.
Mostly we spent our time trying to find documentation for what order the state vector is in.
Oh.
So I think we would have eventually gotten to it.
It's a good thing to know.
Well, and in particular, is it orientation or position first? I mean, it was it was 1000000, but still.
Good. Well, so yeah, so you noticed that the state vector got bigger when you didn't weld the joint. That you might have noticed that, which is because suddenly you could think of actually, there's always a joint between the robot and the world. When you weld it, you're actually effectively removing the degrees of freedom of that joint, so you're making the state vector smaller. Now, what's the size of that state vector? If you plotted the size, you'd actually get a weird number, because right now you had 7 joints and 7 velocities. So you had a 14-dimensional state vector. If you plotted the context with the weld removed, what number would you get?
I got 27.
27, like an odd number. How weird is that, right? It's because it's a quaternion representation of orientation.
Oh.
So the positions have 7 elements, and the velocity of that orientation, the spatial velocity, has 6 elements. So normally you'd expect to get twice as many, or an even number, but that's the case. And I'll talk about that in the kinematics thing on Tuesday. What else so what was the answer? Did people find out where is the hand relative to the base when the robot falls?
It doesn't move.
Doesn't move, right?
Still 1.
Right. It's kind of, yeah, it takes a little thinking of, it's maybe counterintuitive, but the only reason that the hand falls relative to the shoulder when it's welded is actually because the ground is pushing up on the shoulder. If you take that away, the whole thing just falls. There's no reason for the hand to move down below the shoulder, right? Little rigid body dynamics. Cool. And if you did get to play with, just the joints, you'll understand that you'll appreciate that we can just do that automatically next time, because it's a real pain to figure out which joint does what, and that should all just be a function you can call, and we'll get there.
Is there drag in the simulation?
Good. We have had versions of drag where we have aerodynamic effects, like added mass and all that good stuff, but that one does not have any drag. No, you can add it. There's a port for that. Yeah, I think I wouldn't trust the aerodynamic coefficients of the KUKA. It's a funky geometry. Okay, so let's talk a little bit about hands. So so far you just played with the robot with the kind of stump hand. It's delivered that way. It's pretty nice. It's got some ports, so you don't even have to run the wires. You can pick a hand of your choice. Hopefully you pick the right flanges so that you can just run your wires through the robot instead of having cables running out the outside. Almost always you spec the robot, you get one hand on it, it looks beautiful, and then you're like, I wanted a different hand, and then it doesn't go through the ports and you see cables running down the side of everybody's robot. But that's the idea. Okay, so but now you've got a decision to make. It's interesting that the world sort of partitions themselves into camps when it comes to the end effectors, right? Some people, I think, really, you should be amazed at the human hand and how incredible it is. And some people think that you just want to work on robots that have hands that are dexterous in the same way that a human hand is. The one on the left is the shadow hand. It's an awesome, amazing hand. It's the one you saw in the OpenAI video I showed quickly in the first lecture. It's very expensive. That's really the only complaint. And they're fragile because they're complicated. The second one is it's called the Allegro hand. We have that in simulation for you to play with. That is a much lower cost hand. It's basically hobby servos put together, but put together very nicely. It's a little big. You can see the scale between the human's hand there and the robot's hand. Feels a little bit like a mitt, but it's pretty good and on the lower cost side of things. So this is the OpenAI demo doing the cube turning. That's with the shadow hand. Okay, and I think actually the shadow hand got a lot more robust as they worked with OpenAI to make this thing work. But there's a different school of thought out there, which says basically, you know what, if I were to give you one of these little claws from the toy store and send you into the living room, you could do a lot of useful things. So, don't blame the hand. The dexterous hand is cool, but you can make a robot very useful here. It's all about the software. And I think there's some truth to that too. And the video that's become kind of the classic demonstration of this, This is a teleoperated robot. This is the early version of what became known as the PR2. This is the PR1. Okay, it was sort of a concept video. They got the funding for the project at Stanford to make this the PR2 robot, and then which went to Willow Garage. Okay, but they just do tons of really useful, cool things with a claw simple gripper, right? And actually, you can go to their website. There's a bunch of other videos. They have it like getting a beer out of the fridge and opening it. They have it loading a dishwasher. They have like just all kinds of things are super useful with a really simple hand. There's also like a third camp, these people that do novel hands. Okay, so this is actually a bag of like a balloon basically and some coffee grounds, and they put it on the end of a gripper, and they use jamming granular media physics. Okay, so when they vacuum suction on the inside of that, all the coffee grounds pull themselves together, and the thing holds its shape. Okay, and so all they do is release vacuum, suck, and they can pick up basically anything. It's ridiculous. So the beginning of that video has a narration. It's kind of cute. It's like, hands have been confusing people, and it turns out if you just have a balloon and some coffee, you can do everything. So, and it's very gentle, and this was one of the early examples of what are typically called under-actuated hands, or more clever mechanical devices trying to solve a problem. And so, I showed another version of that too, which is this, the version from Soft Robotics, which those of you that are there's a few people from Harvard that are joining us. This was a spin out of George Whiteside's lab at Harvard, where they make these, soft, very compliant grippers that just because of that compliance, they can pick up almost anything. But like I said, it'd be very hard to button your shirt with one of these things or with a jamming gripper. So they are incredibly good for some things, but maybe not as dexterous as the human hand. There's also some work, some nice interfaces between the design of the hand and the way you can do sensing. So this is an example from TRI where there's actually, not only is it a soft hand, kind of like that jamming gripper, but that bubble is actually hiding some sensors. It's got a depth camera or whatever sensors we want to fit back there, and it enables a ton of really cool tactile perception, which we will talk about. Hopefully get a guest lecture for later this term. But there is a hand out there. So I put this in when I was typing it in the notes. I thought it was funny that I'll wait for that to finish. But I went to some conference one point, and they just wanted a clever thing like a break the ice kind of thing to what are you going to put on your name tag? They said, what is your favorite robot ever? Real or fictional, right? That's a tough question. Like I've got every science fiction robot book. That's a hard question for someone like me. So I thought a lot about it. And the answer I gave is actually a super cool robot hand. And I don't know if you guys have seen this, but this is actually early 2000s. It looks just like kind of a normal hand, but it's jacked up. It's got relatively conventional motors, but they took off all the safeties and they run like an irresponsible amount of current through the motors, but for a short amount of time. Okay, so it like would catch fire if they did this for very long, but they got this thing like it's like overclocking your desktop or something, right? And they got these really high speed cameras and really high speed tracking, and they started just doing awesome stuff, right? So a little bit of tactile sensing. I don't think that was the biggest part of what they're doing. All right, it's worth watching a couple of these. Okay, here's dribbling a basketball. So if you guys asked about juggling earlier, here's a kind of like juggling, right? Juggling upside down with contact, right? That's slowed down at a ridiculous rate. The whole thing happened like, faster than we could see. Pen twirling. Who wouldn't want to twirl a pen? That is just so good. throw. They had a whole thing about baseball. I forget if it's in this video, but they have one where they also hit the bat, incoming ball, knotting a rope. But so I know we're asynchronous here, but let me see if I can find. I recommend you guys click through to like 240-ish. Best robot trick ever. The cell phone goes up, spins through the air, catches it just like that. It's really good. The guy who, one of the people that was doing that visited MIT or visited Harvard, but stopped by MIT when he was visiting Harvard. So I got to ask him all about it. And I don't think it worked very often, but that's still awesome. All right, questions about hands? So depending on, what I'm trying to do, I would say for the purposes of this class, I fall into the camp of the simple grippers. We've seen a little bit of both, and we've been thinking about both, but I think there's the sort of science of manipulation is, I think, served by simplicity. There's complexity everywhere in these problems, and anything we can do to fight that complexity is a good thing. So for the at least to start out in the class, we've picked this Shunk WSG gripper, and basically it's got a very simple interface. I think I forgot to put it in a slide, but if yes, the diagram is in the notes, but the inputs and outputs of your robot station have the commands you can send to the EWA, the commands you can send to the gripper. Both the EWA takes a position command, just like it would if it was a UR10 or UR5 or something like this. But it also, because it has this torque control, will allow you to send a feed forward torque. And you're going to play a little bit with what it means to send a feed forward command or just set that to 0. I mean, the key idea, which is no secret, is that basically the real robot, you saw that simulation when the torques were 0. The real robot never does that. The real robot has a controller that's running at the interface. It has mechanical brakes. Even when the power is turned off, it's going to be held in place. So if you send 0 torque to the robot, that's not actually sending 0 force to the motors. It's saying, in addition to whatever the controller is doing to gravity compensate the world, to friction compensate and stuff like this, you can add in an additional feed forward torque. That's why the port name is EWA feed forward torque. And you can send down a position command, which it then tries to servo with a PID kind of approach, but we'll talk about the details of how it servos. It is more nonlinear than the simple PID. The Shunk gripper is just got, we model it as 2 independent links, but the controller just commands the distance between those 2 links, okay? You command the size of the spacing between the 2 links, and you can set a max force. So if you remember in the first teleop demo we gave you, I just had a button which said close your fingers all the way and set a relatively soft max force so that it would just close and stop. That's one of the great things about having force control. And then you can open back up, drop the brick. Okay. We will get to some of the fancier manipulation stuff, I hope. There's some simple examples that we've been working on, even in the plane, that that you can take those Allegro fingers and start working with them. But for the basic operations of pick and place, of opening doors and stuff like this, you can do a lot with a simple gripper. Yes, Tony.
Are there any downsides to the soft grippers that you showed off?
So in the past, I would say that, ironically maybe, that their durability has been an issue, especially when there's a lot of sensing involved. So some people here worked on gel site with Ted Adelson and the like. That was one of the first really brilliant sensors here, where you could put a camera underneath and see everything. And then if anybody's working with Alberto, I see Rebecca's there. So people are working with Alberto's lab. They have Gel Slim, they have versions of this. I think there's lots of different approaches there. We're fighting the complexity of the gripper versus like the robustness, and even trying to figure out what to do with all the information. I think, you know, a big soft bubble, it's hard to do dexterous manipulation like buttoning my shirt. So you also fight that battle.
I think one other thing about it is moving from the industrial world where you have super fine precision, you know exactly where everything is. And so if you pick up something with a rigid gripper, you know exactly where you're picking it up and things like that. And then you know exactly where your load is because of things like that. I think that's, you lose some of that when you start going with any sort of compliance. And so if you're thinking about things from that rigid industrial manipulation context, that same mentality just doesn't work, generally speaking.
That's a really good point. Yeah. Yeah. So if you're trying to do something precision, I mean, that's actually the point that I like about, in some sense I like about it, is you're letting physics do some of the work, but that means you're not in complete control anymore, right? That's a super good point.
Cool. Thanks.
Cool. Any other questions? All right. So it turns out that super overclocked hand, they did Rubik's Cube too. They did it even earlier. So I guess I forgot to make this one autoplay, but go ahead and play that one for yourself. I
We
love that
achieved
hand.
manipulation of
I forgot
Rubik's
to mute it
Cube
too,
using
sorry.
a high-speed robot hand.
Anyhow, pretty slick. Again, I think it might melt if it tried to do that for more than like a minute. But. All right, I'll end there. I'll ask you for your quick exit survey here. We'll do it as much as we can. Tell me what you thought about the breakouts. If you thought you needed more time, less time, anything like that, I want to hear it. The problem set took us a few more hours than we realized, and it went out this morning instead of last night, but it's up and was due next Wednesday. The notes are all up and should be linked. I'll make sure they're linked, and we will see you on Tuesday. I'll stay on if anybody has questions, but thank you very much.